Okay, so in this one, I want to finish up the problem that we started in the last one by thinking now about the second lake. All right, so let's go do that. So we've got this set up. Now I want to think about the second lake. We've finished out the first lake entirely. We know the status of its the toxic substance in the first lake completely. How about the second lake? So now we're going to be asking for, in our differential equation, we're going to be asking about ds2 dt. Yeah? The rate of change of the toxic substance in the second lake. Okay. Well, rate in minus rate out, right? The rate that substance enters minus the rate the substance exits. I'm looking at this key idea here again. So what is the rate at which substance is entering the second lake, rather? Well, that's going to be the concentration of toxic substance in this first lake times the volume of that water that's going into the second lake. And the volume of the water that's going into the second lake is 500 liters per hour. So we should first write the concentration. The concentration is going to be however much is in that first lake of toxic substance, however much of that, which we gave a name to, is S1 of T, right? This is S1 divided by the volume of a fluid in that first lake. That's 100,000. And then we're going to multiply this by the amount of fluid from that first lake, which is entering the second lake. That's 500. Okay, that's the amount of substance which enters the second lake. Now, how much is exiting the second lake? The amount that's exiting the second lake is going to be given by, it's the concentration of toxic substance in the second lake, the concentration that's of stuff in this second lake, multiplied by the rate, the volume of fluid that's leaving that second lake, which is 500 liters per hour. Okay, so first of all, what's the concentration in the second lake? It's the amount of stuff in the second lake divided by the volume of the second lake, which, by the way, is 200,000 liters. And this is multiplied by 500. Okay, so this is complicated, more complicated maybe than what we've seen in the past. If I simplify this by doing some basic arithmetic, I'm going to move this second term, for reasons that I know, to the other side. 500 divided by 200,000, I believe, is 1 over 400. And I've got a negative sign there, so this becomes, I'm going to move it over to the other side of the equal sign. I get 1 plus 1 over 400 S2. Hopefully you can hold that. And then on the other side, I'm going to have, so let's see, 500 over 100,000, we've already said, is 1 over 200. But then we multiply this by S1 of T. What is S1 of T? Well, in the previous video, we discovered that S1 of T is given by this expression. So we get 500 times the exp of negative 1 over 200t. I don't like the way I wrote that t. There we go. Okie doke. Okay. Now, you can quibble. No, you can't. Sorry, I don't know why I said that. But look at it. Okay, it looks kind of messy. But the thing that I want to say is that this is a first order linear differential equation. This is a FOLDE. It's a first order linear differential equation. Crucially, it's linear. Okay, it's linear because do you see S2 prime plus P of T S2 equaling Q of T. Here's P of T. And all this is Q of T. So I know in principle how to solve this, and that's what we're going to do now. Oh, I should say, I forgot. We should also be clear. We know an initial value for S2. S2 of 0, let me erase this. So this is the differential equation, but the initial condition is that S2 of 0, the amount of toxic substance initially in the lake, is 0, right? So that's going to be helpful for us, I hope, to solve to being able to pin down some precise constants. Okay, so we should figure out a integrating factor, yes? Some places call the integrating factor mu, but our textbook, so mu is a Greek letter, it looks like that. So just be aware of that if you ever are looking around at stuff. Maybe they'll use the letter mu for integrating factor. But our textbook uses R. I have no idea what the consensus is, but I know the letter R, and mu, isn't that a Pokemon or something? Anyway, R of t is going to be my integrating factor, and that's exp of, in this case, integral of 1 over 400 dt. And so this is exp of 1 over 400 t. Okay, easy. That part is easy. Now we can write down the general solution. So don't forget, this is going to be given by S2 of t is equal to 1 over r times the integral of r times q dt. In this case, 1 over r is equal to exp of negative 1 over 400 times t. Don't forget the logic there. When e to the 1 over 400 times t is the same thing as that right there. And 1 over it just applies a negative sign to the exponent. Then we multiply this by the integral of, now r times q. So here's q right here. We're going to multiply this by this r right here. First point, 500 times 1 over 200 is 5 over 2. So I'll just go ahead and do that, simplification. And then maybe I'll have us think a little bit more carefully about the rest of it. So this is exp of negative 1 over 200 times t times exp of 1 over 400 times t dt. So we have a product of exponentials. So we should add the powers together. So we get here, I'll pull out the 5 halves as well because I don't want to look at it. 5 halves exp negative 1 over 400 t, that's the first part of me pulling out the 5 halves, times the integral of, now we add the two things together. Negative 1 over 200 plus 2 over 400. What? I should make a common denominator of 400 is what I should do. So this is negative 2 over 400 plus 1 over 400, so negative 1 over 400. dt. And now I integrate. I like putting a big old bracket to remind myself that the plus c that I get out as an additive constant of integration also gets touched by everything outside. And what do I get for that constant? Well, I got to take the reciprocal of negative 1 over 400. I believe that's negative 400. Exp of negative 1 over 400 times t plus c. We see the fancy thing that happens in which this exp and that exp, oh no, what? Do they join forces? Is that what I was expecting? I don't know, maybe. I guess the math is what's dictating that. So we get 5 halves. Oh, and 5 halves times negative 400. So 5 times negative 400 is negative 2,000. Divided by 2 is negative 1,000. Negative 1,000. And then we are multiplying the exps together. We're multiplying this and that together. And what do we get when we do that? Well, we add the exponents together, so we get negative 1 over 200, I believe. T. And then we push the other term to the plus c as well. The 5 halves and the c get married and become a c. the C just completely dominates it. And then we have C times exp of negative 1 over 400t. Okay. All right, good, good, good. And then we can use the initial condition that S2 of t is 0. So 0 is equal to S2 of 0. And what that means is this exp right here becomes 1. That exp becomes 1. So what we end up with is negative 1,000 plus C. And so C evidently is 1,000. So in the end, we know that S2 of t is equal to negative 1,000 times exp of negative 1 over 200 t plus 1,000 times exp of negative 1 over 400 times t. Now don't forget what the problem asked for. I kind of forgot. It's asking for the concentration of the toxic substance in each lake. We have S1 in hand. Where is it? I forgot. Here, where is it? Here it is. I can duplicate it, and then I can move this down, move it even further down. There's my S1 of t. And now I've got S2 of t right here. Duplicate, and then I can move this down here. And then you know what I can do? I can do the following hack. So the concentration in each case, so the concentration in first lake is going to equal to this quantity, which is the amount of toxic substance in the first lake, divided by 100,000. And the concentration in the second lake, oh, this should be red, is equal to this divided by 200,000. And you can simplify, but guess who doesn't want to do that anymore? And doesn't want to deal with this anymore. This guy. Okay. Stay safe out there. The world is getting crazy. I love you. Bye.